Hello everyone, I am Muhammad Ishfaq and my presentation topic is Summary of SWFC-ART, which is a cost-effective approach for fixed-size candidate set adaptive random testing through small word graphs. So these are the contents of my presentation. First of all, I will give background of the research, and then I will present the proposed method, and then I will give the details about experiments and results, and then I will conclude about the presentation by giving answers to the research questions. Adaptive random testing is an extension of random testing, which is based on the motivation that failures in software tend to cluster themselves in contiguous regions. Therefore, if a test case or a combination of test cases are unable to find a fault in software, then next test case should be selected that is far away from the previously executed non-failure causing test cases. In this way, we achieve the even spread across software input domain, and we have more chances of selecting test inputs from failure regions. So fixed size candidate set adaptive random testing is the first proposed ART strategy. Black dots represent the already executed test cases that were unable to find a failure. And now the circles represent the candidate test cases. In the beginning, we calculate the distance of candidate test cases with previously executed test cases, and we find their nearest neighbors. In the next step, we find the candidate test case whose nearest neighbor is at the highest distance from the previously executed test cases. As we can see that the nearest neighbor of C2 is at the more distance has more distance compared with the nearest neighbor of C1, and therefore we select C2 as the test input for our next testing iteration. However, FSCS-ART faces two problems, and we call them double tier efficiency problem of FSCS-ART. The first problem is the increase in computational overhead when number of test cases increase. And the second problem is increase in computational overhead when number of dimensions of input domain increase. So our hypothesis is that if the nearest neighbor search mechanism can be scalable and consistent with dataset size and dimensions, it may alleviate the double tier efficiency problem. So by solving this problem, we looked at several nearest neighbor search data structures, and we found that the small word graphs have the potential to solve the problem of FSCS-ART. On the other hand, small word graphs introduce few long range and short range links in the graph. The short range links connect the nearby nodes, and they provide the local connectivity, and the long range links connect the distant nodes, and they provide the global connectivity within the graph. In this way, they scale down the greedy search to polylogarithmic order, and small word properties can be introduced during the construction of the graph. By construction, we mean that if we connect the nodes with other nodes with random nodes, and by increasing the randomness to a specific level, there will be small word properties in the graph. In this way, there will be small average distance between the nodes and high clustering, compared with regular graphs that have high clustering and high average distance, and random graphs that have small average distance and low clustering. Hierarchical navigable small word graphs are further extension of small word graphs. The main extension is the separation of the links into different layers based on their lengths. So there will be fixed number of layers in the graph and fixed number of connections at each layer. In this way, the overall complexity will become logarithmic. Here is an example of this graph converted to layers, and we can see that the top layer, the dotted line represent the longest range links, and middle layer represent the medium range links and represented by dashed line, and the solid line represent the shortest links. And the search starts from the highest layer and finds the nearest neighbor on the top layer, and then search further goes down and down to the refined stages unless the nearest neighbor has been identified. So our proposed method SWFC-ART, which is a fixed size candidate set based on small word graphs, has 7 major steps. In the beginning, we initialize and hierarchical navigable small word graphs with some parameters that we will discuss in the next slide. And then unless the termination criteria has been satisfied, we generate k number of candidate test cases randomly, and we find their nearest neighbor from the graph. So for each candidate we find their nearest neighbor, and when the nearest neighbor of all candidates has been found, we find the candidate whose nearest neighbor is as the maximum distance, and we select that candidate for the next testing iteration. So when the termination criteria has been satisfied, the algorithm returns a graph, and the nodes of graph represent the test cases that were executed during the testing. For the method to work, we have to set some parameters. For example, number of candidate test cases to be generated, and we set its value to 10, which is consistent with previous ART studies. However, the main problem was the graph size. The graph size has to be given in advance. However, in adaptive random testing, we don't know the number of test cases to be generated. So we ran some simulation by specifying graph size from 10 to raise 2 to 10 to raise 5, and we found that 10 to raise 4 has optimal value. The another solution can be to set the graph size as maximum as supported by hardware software platform. However, this can incur a huge computational cost. Also, the graph size parameter has no effect on the effectiveness of the method. For the distance function, we have used Euclidean distance. For the size of dynamic list, these are the nearest neighbors to be searched on the candidates on the layers that are above the layer where a node is to be inserted. The construction parameter is the number of nearest neighbors to be searched on the layer where a node is to be inserted, and the below layers. And number of links are the number of nodes to be connected to a node, to the newly inserted node. By setting high value of these parameters can increase the effectiveness of the method, and however there will be a trade-off with efficiency. This is an example of the proposed method. Here we can see an initial HNSWG, and suppose that a node 7 is to be inserted at layer 1. As we know that the value of EF is equal to 1, so therefore at the higher layer only one nearest neighbor is to be searched, that is node 4. So on layer 1 the search starts from node 4, and now 3 nearest neighbors will be found for the node 7. So the nearest neighbor for node 7 are 5, 4 and 2. However, here there is a problem that if the node 7 will be connected to the nearest neighbors. However, node 4 will have 4 connections, and as we can see that for the m parameter, node 4 can only have 3 connections. Therefore the connection between node 4 and 6 will be trimmed, and at the bottom layer also node 7 will be connected to its nearest neighbors. Now suppose that node 8 is to be inserted at near layer 0. It means that when a node inserted at layer 0, and now its nearest neighbor is to be found on only one nearest neighbor is to be found at the higher layers, which is node 6, and on layer 1 here is node 5, and on layer 0 its 3 nearest neighbors are found and are connected. So in the end, this is our updated hierarchical navigable small word graph. Talking about complexity analysis of the proposed method, the construction time complexity of the graph is n log n, and the nearest neighbor search time complexity for one candidate is log n, and for k candidates and d-dimensional input domain, and for n runs it also is log linear or quasi-linear. For storage complexity, it takes only 4 bytes unsigned integers to accommodate 4 billion test cases. So we designed our experiments based on these 3 research questions. The first one is that does SWFC-ART successfully solve the double tier efficiency problem, and how effective is SWFC-ART at revealing failure, and how evenly does SWFC-ART distribute test cases. So our experimental setup is based on These four evaluation metrics. Test case generation time is the time taken to generate a specific number of test cases. Test case execution time is the time taken to execute a specific number of test cases, and this is applicable to empirical studies only for real life programs. Discrepancy measures how evenly test cases are spread across software input domain, and F measure is the number of test cases to be executed before finding the first failure. We have compared our method with FSCS-ART and Limbal KDFC, which is a KD tree based enhancement of FSCS-ART, which stores test cases in the KD tree based data structure. That paper proposes three new methods. However, the limited backtracking and balancing strategy of KDFC-ART, which is Limbal KDFC, showed better results on high-dimensional input domains. We have conducted empirical studies on 28 real-life programs of different sizes and dimensions, and we have also conducted simulations by simulating block, strip, and point failure patterns of different failure rates and different dimensions of input domain, and we have also generated test cases of different test suites of different sizes and different dimensions of input domain. Here are the efficiency results in simulations, and we can see that from 2-dimensional to 4-dimensional input domain the results are similar. In the first place, FSCS-ART has huge computational cost, where x-axis represents the number of test cases to be generated and y-axis represents the time taken to generate those test cases. We can see that FSCS-ART has quadratic time cost, and it becomes worse and worse when the number of test cases to be generated, when more number of test cases to be generated. However, Limbal KDFC performs best, and our proposed method performs similar to Limbal KDFC with a little worse results. However, when the number of input domains increase, for example on 5D input domain, the results of FSCSC performs same. However, Limbal KDFC and SWFC performs almost similar. And when on high dimensional input domain, for example 10D at 15D, Limbal KDFC starts showing worse results, and its time cost starts increasing. However, our proposed method still shows is still consistent on high dimensional input domain, and it still has low computational cost. Same phenomena can be seen on the real life programs. For example, till 6-dimensional input programs, Limbal KDFC shows better results. However, on high dimensional input programs, large programs, our method shows better results. In terms of failure detection effectiveness, our method and the rival methods show almost similar results. The p-value and effect size show that there is no significant difference between the results, and we can conclude that the effectiveness of our proposed method is almost similar to the previously proposed methods. The discrepancy results of SWFC-ART is not much different from the Limbal KDFC and FSCS-ART. So the answers to research questions is that because real life programs may often have low failure rates and high dimension input spaces, neither FSCS-ART nor Limbal KDFC solve the double tier efficiency problem. In contrast, SWFC-ART's consistency and scalability, regardless of number of test cases or the dimensionality of input domain, make it the preferred method. SWFC employs a unique approximate nearest neighbor search strategy, and its failure detection effectiveness is comparable to that of the state-of-the-art method KDFC-ART. And the answer to research question 3 is that SWFC-ART distributes test cases as evenly as state-of-the-art method KDFC-ART, even though it employs approximate nearest neighbor strategy. Thank you for your attention.